So how then do we find chi for a given delta t? We start once again with chi dot is equal to root mu over r, and we can set up a Newton-Raphson iteration on the function f of chi is equal to root mu delta t minus the integral of r d chi. Because recall, this right here is exactly how we got our previous value for root mu delta t. This is in fact that marked expression all the way up here that we labeled with a text dagger. We got this by integrating r d chi. Therefore, this function has to equal 0, and so we can use it to do our iteration. We just need to find the first derivative of this function in terms of chi. So f prime of chi is df d chi, and will just equal negative r, because these are constants, and we are taking the derivative of the antiderivative of r. Therefore, our Newton-Raphson iteration for chi looks like where we have just plugged in our previous definitions for these expressions, and the sign here flips because of the negative on the denominator r. Okay, so we can do this iteration, but we need an initial value. How do we get the initial value of chi? Well, let's go all the way back to our r expressions. And let's start with the radius for an elliptical orbit. The orbital radius for an ellipse is equal to the semi-major axis times 1 minus the eccentricity times the cosine of the eccentric anomaly, which in our previous derivation, we know we can write as the semi-major axis times 1 plus the eccentricity times sine of chi plus that constant of integration c naught over root a. We solve this for negative e cosine eccentric anomaly is equal to e sine chi plus c naught over root a, which we can rewrite as, recalling that sine and cosine are a 90-degree phase shift away with a change in amplitude by a factor of -1. So we eliminate the negative e's, we eliminate the cosines, and we have eccentric anomaly is pi over 2 plus chi plus c naught quantity over the square root of a. This means that if we look at the change in eccentric anomaly between a time t naught and a time t, we have pi over 2 plus chi plus c naught over root a minus quantity pi over 2 plus chi naught plus c naught over root a. And as before, we take chi naught to be 0, which means that all of this stuff cancels, and all that's left is chi over root a is the change in eccentric anomaly for the propagation between a time t naught to a time t. In the exact same fashion, for hyperbolic orbits, we will find that chi over the square root of negative a will be the change in hyperbolic anomaly. And you can verify this by just going through this entire process, but plugging in the relevant equations for hyperbola. For parabolas, a is infinite, which means that psi is 0. And this means that our C2, C3 quantities are going to be exactly equal to 1/2 and 1/6. And therefore, r will just equal chi squared over 2 plus r naught dotted into v naught over root mu chi plus r naught. R naught dotted into v naught, which equals r dot, in this case will be the square root of mu L times Barker's anomaly. And recall that in the parabolic case, the orbital radius is equal to the semi-parameter over 2 times 1 plus b squared, the parabolic anomaly squared, which means that we can directly solve for chi as chi equals the square root of the semi-parameter times the parabolic anomaly. So we can map chi to the anomaly for any orbit. And to get the initial conditions for the Newton-Raphson iteration on chi, we just need to crunch through the algebra on the orbit-specific conditions for each orbit type, and they have the following forms. So chi is root A delta E, or root L delta B, or negative root A delta H. Chi naught is initialized as root mu delta T over A for closed orbits, root L tangent of B naught over 2 for parabolas, and this horrible expression here for hyperbola. The Newton-Raphson iteration on chi naught has this form that we've previously derived with C2 and C3 defined on the previous slide. And our friends, the f and g function, have a single universal formulation in terms of chi. We have now provided ourselves with a true universal variable formulation. Chi is representative of all orbit types. It requires much, much less bookkeeping in terms of checking for whether you're on an open or closed orbit, and has a unified set of equations with logical branches only in the initialization of chi naught. We can also fairly simply convert back from chi into the various anomalies that are more geometrically intuitive. And so this is a really great option for propagating orbits. And this is something that we're going to be using later on when we look at the orbital boundary value problems.